Hey, today we're going to talk about voltage comparer, aka a comparator. And to ease the task of showing that, I'm going to use Radioshack 130 in 1 electronic project lab. So this is the manual. This one is very nice because it has a, I hope you can see my marker here. Yeah, so here it has a dual op amp, and op amps are very interesting in electronics. I think it's much easier to deal with than transistors, like for doing amplification of signals. So that's a good one, and on top of that it has a speaker, so that's pretty cool. All right, so next look at the next slide. So this is the comparator, and this is a circuit we're gonna study, if you will. But I think I'll get back to that later. First, let's see how it looks like. What happens is that when there's a switch here, that's your op amp, and it's the output. This is the output, goes into an LED here. So if the switch is in the A position, the LED lights up, and if it is in the B position, the LED is turned off. So that's the whole thing. And why it's called a comparator, it's because if the voltage at 69 here is greater than voltage at 68, the output is going to saturate. And if the voltage at 69 is less than 68, you're going to have zero output. Hence the LED is not lit up. But, okay, so I think here the switch is on B, and I'm going to push it to A. Yes, and the LED lights up. That's right. So now, I'm overdubbing this, so it's kind of awkward. So now I think I'm going to measure some voltages, and the way to do it is with crocs. I mean, crocodile wires. Otherwise, you're going to get weird readings. It doesn't register right on those spring things. So you put the negative on the battery negative, and the positive here, I think I'm putting it on the reference voltage, I believe. Yes. So 3.9, and then I'm gonna go into the input voltage, which we are comparing with the reference voltage. Sometimes it's hard to get them out. So now this is the input voltage, and it should be greater. That's why the LED lights up. So that's how it works. So now let's do something else. All right, let's talk about op amps first before going into that circuit. And here I'm talking about open loop, as opposed to closed loop, and we'll talk about closed loop as well. So a typical op amp has a very high amplification, like 10,000, 50,000, something crazy, and also it has a very high input. There's a very high internal resistance here between the plus and the minus. So anyway, this is your op amp. There is a positive voltage for the supply, negative supply here. So plus 12, minus 12. This is the output. It goes through a load. This is the ground, and this is your non-inverting input, and this is the inverting input. So minus for inverting, plus for non-inverting. And basically, if you want, you can just put your input right there. It's a differential input in this case. Anyway, so the interesting thing is that if V in plus, this one, is greater than V in minus, that one, even by a fraction of a millivolt, V out is going to saturate. So in this case, if I have 12 volts, it's going to be around 10 volts. And if V in plus is less than V in minus, even by a fraction of a millivolt, V out is again going to saturate, but this one on the negative side, so minus 10. So this is a comparator. It compares, this is your let's say this is your reference voltage, and you put an input voltage here, which is either greater or lower than this reference voltage, and you get either plus 10 volts here or minus 10 volts. In the case where you have 12 volts here and ground here, you would have 10 volts when this one is greater than that one, or 0 volt if it's the opposite. So that's why it's called a comparator. You can compare two voltages, and it's used a lot in like a logic circuits. Okay, so now let's move on. So that's one way of using a op-amp. But there is another way, which is amplification, of course, of like audio signals. Okay, so let's look into the inverting amp. So now it's a closed loop, and the expected amplification factor is going to be much less than 10,000. So now it's usable. And this is called closed loop because of this feedback loop between the output going back into the input. So in the case of the inverting amp, you have the so the plus input is connected to ground, and the inverting input is connected to your input signal, which goes through a Ri, which is an input resistor, and this is the RF, the feedback resistor. This is again your load. This is the output. So the input looks like this, like a sine wave, and this is the output, inverted and amplified. So what is the amplification factor? It's equal to Rf over Ri. So Rf over Ri. And what is the input resistance? It's Ri. And what do I mean by input resistance? It is, if you look at this like that, plus minus, you have your Ri. And if you put your I here, that's your I, okay, with the I, like this is your I, this is the resistance you see. So this is R in. That's the resistance you see from the outside, going in. Okay, so this is an inverting amp. And you have the same thing on the other side. And this one is a non-inverting. The only difference between the inverting and the non-inverting is how you, those two here. I've basically switched those two things. V in was here and the ground was there, and I switched them around. But other than that, it's the same thing. You have your input resistor, you have your feedback resistor, the load, and this time the input is on the non-inverting input. So this is your input and this is your output. No inversion in this case. The amplification factor is Rf over Ri plus 1, and the input resistance, so plus minus, this is the out, this is the input side, okay? The input resistance, when you put your I here, go looking in, the only resistance it sees is the resistance here, internal resistance, which is very high, so it's infinite. So this is very good. So this is the non-inverting amp. Maybe I should have done something. Let me just quickly, because I forgot something. An interesting follow-up. An interesting follow-up is the same thing, op-amp closed loop. But this one we're going to do a voltage follower. So it looks like this. So you have your plus, your minus, your out. Same thing. So this is your V out here. And same thing, you have your input on this here. And this is your... but here you don't have a Ri. The feedback loop looks like this. So basically RF is equal to 0, and if you draw RI, it's actually infinite, because here there's no connection to ground, because it was connected to ground before. So you just get rid of all this, meaning that RI equals 0. It's open. RI equal infinity, sorry. So it means that AV, which is equal to RF over RI plus 1, is now equal to 0 over infinity plus 1 is equal to 1. So there's no amplification. And Rin is still infinite. So this circuit, even though it doesn't amplify the voltage, it basically in a way amplifies the current. So it's great as a buffer. It's great as a buffer. So if you have, let's say, a voltage source, and that voltage source has a internal resistance which is not small, it is, and then if you wanted to connect this thing into a RL which is small, so if RS is much greater than RL, there's going to be a huge voltage drop here, and you're going to lose a lot of power here. So in order to avoid that, here you put the buffer amplifier or voltage follower, whatever you want. It's a buffer, and then you have no problem in terms of impedance matching. So I just wanted to say that it's very important to know that circuit voltage follower. Okay, so now let's go back. Okay, so I'm back to that thing. Okay, so here we go. So now it's much nicer. Okay, so let me explain that circuit. So here you have your ground. And this is the top of the, so this is the supply, the power supply. So this is happens to be 9 volts. Here on the negative supply you have 0. So you have 0, 9. And here you have a reference. You have a reference voltage. You have a reference voltage. And it goes through a voltage divider. Okay, so it has 4.5 volts here. And here you have a voltage divider with that 2.2 and the 10K. Okay, so I think the voltage is about 3.9, I believe. I wrote down the actually I can just go there. Yes, so V68 is 3.9. V68 is 3.9. And assume that the switch is on A, which is correct. So we have 3.9 here. So the switch is on A, so you have 6 volts here, and again you have a voltage divider, 1K, 10K. So here you have a voltage drop of 0.6, I believe. So you should have 5.4 here. Let me check on 69. 5.8. It's probably because I don't have actually 9 volt, but probably 9 point something volts, since I have fresh batteries. So okay, so in this case, V, the voltage at the plus is greater than voltage at the minus. So what's going to happen is that the output is going to saturate, and the voltage here at 67 is going to be pretty high, close to 8 volt, I would assume. Let's see, 67. V31, hold on. Oh, it's the same thing. So V31 is what? V31 is 7.4. Okay, close enough. So it's saturating. So it's not 8 volt, it's 7 point something. So, and that lights up the LED, the LED. No problem. So now what happens when you switch? You switch to B. So now you have, so this doesn't change. The V68 is still 3.9, but this one is going to change because here you have 1.5 volts. And it's going through that voltage divider again. And here the voltage drop is going to be 0.15 volts. So you're going to end up with probably 1.2, 1.3 volt on 69. Let's check on 69. On 69, I'm getting 1.5 volts. So 1.5 volts here, 3.9 here, so the V plus is less than V minus, so you're gonna get 0 here. If we assume that you had plus 12 here and minus 12 here, you would get minus 10 around minus 10 here. Well, that's really all there is to know about this circuit. There's nothing more to say about it. Okay, yeah, so when you build it, try to write down the voltages that you see. So here I did the switch on A, the V68, so this is the reference voltage. V69 is the voltage on the inverting input. That's the one we want to compare with the reference voltage. And the V31 or 67 is the output voltage, the one that drives the LED. So switch on A, you get 7.4 volts. So the LED lights up, otherwise you get 0 and nothing happens. Okay, I think I'm gonna stop here and I'll see you around. Bye.